Welcome to 1.6.2. Three more examples for integrals involving exponential functions. We'll start with example number 2. Evaluate the following indefinite integrals. And pretend that's an e. That's half of the example. It's just pretending that's an e. Part A is going to be the integral of 3x squared e to the 2x cubed. Again, this is a perfect example of what we're looking at in this chapter, especially in the previous section. We can't take the integrals of this individually. They're being multiplied. When integrals are multiplied, when the integrand is two functions that are multiplied together, one of the options is u substitution. Another one that we'll talk about later is integration by parts. We have an exponential function, and if we look at what's on the inside of this exponential function, we notice that something that's on the outside is very closely related to the derivative of what's on the inside. That's what you always want to look for u substitutions. And maybe you didn't see it, but this is still the best thing to try for a u substitution. Try to let u be the inside. If u is 2x cubed, well then the derivative of u with respect to x is 6x squared. So du is going to be 6x squared dx. Well, too bad. We almost have it. Well, we can get it. We can get a 6 by just multiplying by 2. But if we multiply by 2, we should also divide by 2. Remember, there was also another method where you could take this boxed guy and solve for dx. That's usually more straightforward, but more steps. If you want to solve for dx here in this boxed area, you can do that as well. Or you can just multiply by 2 and divide by 2. So if we do that, we get 1/2 integral, let's see, 6x squared dx. Everything in blue just becomes du. The only thing left is this green guy. And this green guy is just e to the u. Well, we know the antiderivative of e to the u is e to the u is just itself. That was one of our rules. And then again, technically, right, this 1/2 gets distributed to the constant, but we never write that because half of any real number is still just any real number. And then we get our final answer by replacing u, and we can check our answer by taking the derivative. We take the derivative, the derivative of an exponential function is itself. We have to use the chain rule here, so we multiply by the derivative of the inside, which is 6x squared. Half of 6 is 3. Derivative of a constant is 0. And we indeed get exactly what we started with in the integrand. Same thing. And that's how we check our answer here. Okay, 2 more. Let's get into some more fun ones. And we do even more fun ones in the selected homework problems video of this section, but let's show that you can also do this with definite integrals and then do one that's a little bit more fun. Actually, we don't have any super fun ones in this video. 1.6.5, that's where the super fun ones are coming, okay? Integral from 1 to 2 of e to the 1 minus x dx. Remember, you can do u substitutions with definite integrals too. It's going to be the same idea here. I'd recommend that you pause the video right now and try to do this problem as well as the next problem on your own. The next one will be 1 to 2 e to the 1 over x squared dx. So try to pause this and do both of these and see if we get the same thing. So we can't take the derivative if there's an inside function. We have to use u substitutions. Sorry, when I said derivative, I meant antiderivative. And technically it's possible, but you have to really make sure that you get the right answer. Take the derivative here, we get -1. So du is just the opposite of dx. And we can make that as long as we just put that negative in there and balance it out with another negative. Negative times a negative is a positive, which is not true for people in real life who are negative. But in mathematics, it's true. So we get negative, the integral. Oh, we're doing a u substitution. The limits of integration, we're going to update those too. If u is 1 minus x, then when x is equal to 1, what happens to u? If x is 1, u is 0. And if x is equal to 2, what happens to u? U would be negative 1. And again, it's okay that the smaller one's on top here. That's fine. Integral from a to b doesn't have to have a and b in order. The blue stuff just became du, and we're just left with this yellow stuff, which is just e to the u, because u is 1 over x. They're the same thing. Now we can evaluate this antiderivative. Antiderivative of e to the u is itself. And we don't have to substitute back into x because we already updated our limits of integration. So we get e to the negative 1 minus e to the 0. Remember that this is not 0, this is 1. We're going to distribute that negative and get negative e to the negative 1 plus positive 1. Or 1 minus 1 over e as our final answer. And we're going to check our answer by taking the derivative and see if we get what's originally have. So this is a constant. Derivative of a constant is 0. What happened? We're supposed to get this back, right? So this is not something I made a mention of very often, but you can't check your definite integrals this way. Right? A definite integral, we can think of definite integrals as the area under the curve. A definite integral, if the limits of integration are numbers, is going to be a number. And so this definite integral is always going to be a constant. So its derivative is always going to be 0. You can only check your answer for indefinite integrals in that fashion. There are other ways of checking your answers for definite integrals here, but just note that I want you to check your answer by taking derivatives, but if your answer is just a number, then that's not going to be very helpful. The other one was very similar. It's not super clear what to do first here, but if you notice that this is our inside function, and when you take the derivative of 1 over x, you get negative 1 over x squared. That looks very promising. So let's let u be 1 over x, which if we'd like, we can write it as x to the negative 1. Well, then its derivative is just what happens when you apply the power rule. And I said that you have to watch out when the exponent's negative 1, but that's for antiderivatives. The derivative when x equals negative 1, no problem. The antiderivative when x is, or when the exponent's negative 1, that's when you got funny business. So du is just going to be negative 1 over x squared dx. So let's rewrite this inside a little bit before we move on. If we write it like this, 1 over x squared times e to the 1 over x dx, you can see more clearly what's happening. Because these two things are exactly the same, right? Well, now we almost have du. Du is negative 1 over x squared dx. Well, all we need is a negative. So let's use the right color to be consistent with what I've been doing. And now this blue stuff is just du. Let's update our limits of integration. If x is equal to 1, that means u is 1 over x. It's still 1. If x is equal to 2, u is 1 over 2. 1/2. And now everything in blue becomes du. That rhymes. And all that we're left over is this green guy, which is just e to the u. Antiderivative of e to the u is itself, evaluated from 1 to 1/2. Remember, we already updated these for u, so we don't have to go back to x. We get negative e to the 1/2 minus e to the 1. Make sure to distribute that negative. And there's a couple ways of writing your answers, but I'm going to write this as e minus the square root of e. Distribute that negative, puts the e to the first power in the front with a positive. And exponent of 1/2 is just square root. As a reminder, one of the ways that you can check your answers on these is with Desmos. Take the integral without capital letters, the integral from 0 to 1 of e to the 1 over x divided by x squared dx from 1 to 2 from 1 to 2 is about that. Is that e minus the square root of e? Well, looky there. Great. That's it. That's this problem. That's this video. More examples. Again, there are some trickier ones in the homework. I want you to apply what you've learned here, apply the problem solving strategies. And specifically, the big part of these homework ones is going to be, can you get a good choice of u? Because it's not always going to be super obvious, but hopefully I talked you through the logic. And if you want more help, well, that's what video number 5 is for, selected homework problems. Good luck.